Hello there and welcome. Today we're going to be talking about linear and nonlinear regression and how we can use those to fit some vapor pressure data for water. Alright, let's get started. So we're going to be using the Antoine equation today, so I'm just going to go ahead and write that down. So it's log P is equal to A minus B over T plus C. All right. So we're going to go over the linear regression part first. And we're going to be using Python to do this to make it way easier for us in case we want to switch out chemicals or something of that sort. So first thing we're going to do is manipulate this equation so we can apply some linear algebra using matrices. So we're going to go ahead and multiply the t plus c to both sides. And then we get minus b. All right. I'm just going to go ahead and expand that out. Log p is equal to AT. Whoa, that's a mistake. All right, so then we're going to move over this portion over here so we can get the log of the temperature by itself. And then we've got AT minus C log P plus AC minus B. And then to make it easier in Python, we are going to take this and we're going to call that D. And so a little later on, we're going to want to know what B is because that's the only variable that we don't have by itself. So we're going to go ahead and just solve for B right away because this is really D is equal to AC minus B. So then we're going to go ahead and solve for B. We've got AC minus D. All right. So let me get us some more room here. And now we're going to build our matrices. So the way we're going to do this is we're going to have our temperature data in one column. We are going to have the negative log of P in another column. And then we're going to have a row of ones. And this is our design matrix for the matrix multiplication. And so we've got T2, negative log of P2, and then another row of ones. And we're just going to, this is a 3 by n matrix here. And then we also need to know the values for A, C, and D. So that's going to be a 3 by 1 matrix with A, C, and D in it. And so this will result in a matrix with the temperature and the pressure in it. That's a 1. And there we go. All right, so we are going to have to do some manipulation because right away it looks like we've got this n over here and we can't multiply that by a 3 by 1 initially. So we're going to have to do some manipulation. And what we're going to need to do here is we're just going to rename all of this. We're going to call this x. And then we're going to name this, and we're going to name that little v. And then that's going to be equal to, we're going to call this, I'm going to call that y. All right. So because this is a 3 by n, and this is a 3 by 1, and this is a blanking on what that is. That's a 1 by n. Sorry, blank there. We need to do some manipulation. So to make this into a 3 by 3 matrix, we are going to multiply by its transpose. And so that's just an n by 3 matrix. It's got three rows, and they're just going infinitely to the right, not infinitely downwards. So we're going to write that as xt times x, and because we got to do it to both sides, we're going to have that equal to y times xt times x. And this is a matrix multiplication here. So let me get us some more room here. All right, and then because we want to find v, because v has all of the variables that we're trying to find, a, b, and c, in this case a, c, and d, we need to get rid of it, and conveniently, because we have this here, we can just multiply by the inverse of the transpose times x, and then we will end up with this here times x transpose of x minus 1. And what this will do, oh, I'm missing one here, sorry. This will all cancel out right here, leaving us with v is equal to y times transpose x times matrix x, awkward parenthesis there, times the inverse of that expression here. Alright, so now I'm going to go jump over to Python, and we are going to code this up. Oops. Alright. So, the first thing we're going to do is we're going to use this command here, wget, to grab our data from this GitHub repository I found that has some water vapor pressure data in it. And we're going to go ahead and open up the raw form of this file and copy the address, and then plug it in here. And after a few seconds, because of the slow internet, we end up with the file that we're looking for in our notebook. So, since we're doing linear algebra here, we are going to need NumPy. So I'm going to go ahead and import NumPy as np. And then we're also going to be graphing some things. So I'm going to get plotly in here, from plotly, dots of plots, import, make, alright, sorry about that, just had to remember it all. So that'll allow us to make subplots within our code here, and it defaults to a white background, and as you can see I'm using a dark background here, so I'm going to go ahead and change that background. So let's see if I can remember exactly how I do that. So import plotly, so that's plotly IO is just the input output of plotly, and then we're just going to rename that because I don't want to have to retype it, and then we're going to do pio dot templates dot default, and then we're going to set the default equal to plotly dark. All right. Perfect. So now we've got a lot of the things we're going to need. So we are going to go ahead and load in the data. So we are going to do that using a NumPy feature called load text. And what that's going to do is it's going to load from files that we have in our notebook. And so we're just going to go ahead and copy that, save us a few seconds here. All right, so now we have the data. Oh, we don't have the data yet. One second, I'm going to fix this and then I will be right back. All right, I see what I did wrong now. I only put in half of what we needed, so that just, we got the data, but we didn't tell it how we wanted the data to be separated. So because it's a comma separated list, that's what .csv stands for, we need the limiter in here. And what that'll do is it'll know, what this tells it is to separate the data points, like the data is separated by commas here. That's why we were getting the comma error down here, because it couldn't separate them, because the comma made it not an integer. Alright, so now we can go ahead and separate the data from just like one big file down into two different variables, the temperature and the pressure. So we're gonna do data and then we're gonna splice it. Got the comma, and then the 0 is just the first column, and then we want log p. We're gonna set that equal to, and because we want the log of the pressure, we're going to do numpy dot log 10 not times in parentheses data, then the brackets, and then we're going to splice it again, 1 for the second column, and we have our data. Now I'm just going to go ahead and plot the data really quickly. We're going to do subplots, and we want one row and one column. So, all right. So now we're going to actually make the plot, and we're gonna add a scatter plot. And we want to set x as temperature as our x variable, and we want our y variable to be the log of the pressure. And then I'm just going to go ahead and actually we want them to be data points, not lines. So we're going to set the mode equal to we want points. Markers, that's what it was. Couldn't think of it there for a second. And then we just want to go ahead and name the data points, so we're gonna create a legend for us. We're gonna set the name of the data to data points. Really creative. All right, did not do something right. I might have forgotten a comma up here. Yup. Got the comma, so it didn't give us any data. Let me just update these. There we go. Now we've got it. And it's a little wide for my taste, so I'm going to update the layout. Update the layout, and we're going to set the height to, let's say, 600. And then we want the width equal to, let's say, 900. I think that'll work out pretty well. And then update that, and there we go. Now we've got a nice little plot. So now we want to actually bring in the data as matrices. So the way we're going to do that is we're going to use big X like we did on, let's open up the note sheet real quick. I want that to be the note sheet. So now we can look at our data if I just zoom out. Alright, so now I can see our data a little bit better, or our notes a little bit better. So now we're going to make the matrices. So as we can see on our notes, we want matrices. The Python command here is, we're using numpy again, so numpy c underscore. That lets us make, put multiple columns together, because we need a 3 by 1, a 3 by n, all the matrices. So we want this to consist of t, negative log, can't forget the negative, of p, and then we also want a row of ones. And numpy lets us do this really easily. It lets us do this command here, lets us put as many ones as t has rows. So it'll put in as many as it needs there. Go ahead and load that in. And now we're ready to do the matrix multiplication. So since we canceled this out, we don't need to do anything with that. But our variables here, a, c, and d, we can go ahead and put those in there. So we're going to call them a, it's going to be a underscore linear regression, just so later on when we're doing nonlinear I can tell them apart. I need c, linear regression. Ooh. And D, linear regression. Hold on, I think I might have messed up the recording. Nope, still going, perfect. And then we are going to set that equal to our matrix multiplication now. So, to do that, we are going to just go ahead and do x dot t, that's the transpose of x, and then we need to do a matrix multiplication. We use the @ sign. Times just regular x, and I'm going to throw them in parentheses just so it looks pretty and I can keep track of it. But we also need the inverse, so we need to use another numpy command. So we've got linear algebra, and then I believe it's dot inverse. All right. And so what that does is that takes the inverse of our matrices here. All right, and then we need to multiply that, a matrix multiplication of that, times, again, the transpose of x, x dot t, times x. And then we also need to multiply that. I think I made a mistake here with the algebra. Y of t, we multiplied x transpose, and then we multiplied by, group those together, multiplied by the inverse of that. Okay, sorry. Just wanted to make sure we were doing everything right. And then we need to multiply that by y. And y consists of two different variables. We've got our temperature and the log of our pressure, and when we multiply those two together, it's just a vector multiplication, so we don't need the @ symbol, we just need log p. All right, just make sure we've got all the parentheses here, and all right, we messed something up here. All right, it looks like I messed up something with our commas. No. All right. So that means I messed up with our matrix multiplication. One mismatch, quarter measure. Okay. Oh, we did make a mistake here. Alright, so this is just the transpose of x here. If it would erase. Alright, so this is just x times transpose of x, right? No, the x isn't there, so it's just transpose of x. Alright. Sorry. Alright, we're just going to leave that there. Got x transpose there, so then this isn't here, and that isn't there. So, because if we would have had that, then these would have canceled, and that would have been wrong. So, pretty big mistake, but we're going to keep going anyways because it's easy to fix here. Yep, looks like I already fixed it. So if we do this, perfect. Now it works just like I intended it to. Alright, so now as we were talking about earlier in the video, we're going to go ahead and solve for b because we know d. So we're going to do keep the same naming system going, and we're going to set b underscore lr on the linear regression of b, and we're going to set b equal to a times c. Let me just throw in a few spaces so it just looks better, and then we're going to subtract from d. Alright, and now that we have what was limiting us before, we have our variables, we can go ahead and plot it all again. So we are going to create another scatter plot. And yeah, so we want our x variable here to be equal to the temperature. And then we want the y variable here to be equal to the right side of the Antoine equation. So we want our a minus our b divided by our t plus c. All right. And then we want to, since this is going to be like connecting our data, we want it to be, we want the mode to be linear? Yeah, lines. We want the mode to be lines, and then we also want to name this, we'll just go ahead and name it, forgot it, equal sign there, would have given us an error. We go ahead and name it fitted linear regression. And then I'm going to go ahead and fix my mistakes. I think I might have messed up the commas. No. Oh. I was talking and typing when I was speaking. Alright, so now we've got our plot, our fitted linear regression data looks good, but we see that the lines are just connecting our data points. It's not like a nice curve. We don't know the good, with perfect accuracy or better accuracy, what pressure would lie at, say, 375 degrees. So we are going to go in and add in a little line of code that lets us expand upon our temperature values, because now we just want more temperature values to make our data curve look like more pretty. It's probably a bad way of saying it, but it makes enough sense. So the way we're going to do that is with the numpy command linspace. And so what this is going to allow us to do is space out our values equally, as many as we have, from a certain defined amount. So we're going to use the minimum values of our temperature, and we want to go from the minimum to the maximum values of our temperature data, and then we want, say, 100 data points. And so that doesn't do anything by itself. We just want to add that in there, and I don't want to put it on this scatter plot. I want to make a new one so it has its own name. And all we have to do is change our variables to fit the temperature variables. And then we're just going to call this our linear regression. Linear regression. All right. And now, as you can see, we have two different lines and then our blue pointers. So here is where I'm going to stop, and then we're going to switch gears. Alright, so now we're going to do the non-linear regression. So let me get some more space here in the notebook. I'm just going to move that over, and then I'm going to copy over the Antoine equation just so we have it to look at. Log p a minus b over t plus c. Alright, and so as we see on our curve on the right, we've got our model, and then we've got data points. And what we're trying to do is fit this model. This model is fit to the data. We want it to be as close as possible to the data. And so to fit the data, we want all of these little differences between our points in the model to be as small as possible. So the way we do that is we take the sum of the difference between the model and our data, right? The data and how far away it is, and we want to do this for all of the data. So what this will do is, so this is our model, and then this is our points and how far away they are. So this is the difference between the points and the data. And so we want both points. We want points above and below. They both are equally significant. And because we don't want them to be negative, we're going to go ahead and take the square. And so this will let us fit our nonlinear data. This is called the sum squared error. It's taking the sum squared error of the data. So now we want to go ahead and type this all into Python. So the way we're going to do this is we're going to go ahead and define it as a function. We're going to call it sum squared error. And then we're just going to call the result, because we want a, b, and c. We used v before, so let's go ahead and use v again. Oh, I forgot the colon. Got to make sure it's a function. All right. So what are we trying to find? We're trying to find the a, b, and c values. And so we want those, we're trying to find those from v. All right. No, not vars, v. All right. And then now we need to have it go through and return our function, or return the values. Return. So we need to type in our equation now. So since we're taking the sum, we're going to use numpy's sum function, and then we need to type in all the data. So we want log p minus, we've got what, a minus b divided by c plus t. And we use t plus c. So let's go ahead and keep it consistent. All right, and then since we need to square it and make sure we get it all, I'm going to go ahead and add in another set of parentheses. So we see this parenthesis connects there, and I'm going to go ahead and use the double asterisk, because that is how we raise things to powers in Python. And then we're going to go ahead and close the brackets. So now everything there is squared, and it fits our equation that we have over here. Shift Enter, everything worked. Perfect. Okay, so now that we have the function and we have the data, we want to go ahead and I'm blanking, hold on. We summed it, we set up the equation. Oh, okay. So I remember now. We need to, because this gives us the difference, but because we want this data to fit, we want the regression to fit as close as possible to the data, we want to minimize this sum squared error. So we are going to use, it's called SciPy Optimize Minimize, and it's already coded and our notebook already has it in it. So we just have to go and call upon this function. So I'm going to come back up here to where we imported everything, and I'm going to get it from SciPy. We need SciPy. We need optimize. So we're optimizing this function. Optimize, and then we want to import minimize, because that is what we're trying to do. Perfect. Go through and make sure we ran all that. Just make sure everything runs perfectly. We're going to restart and run all. All right. Perfect. So now that we have the minimize function in, we're going to go ahead and use it. But because we're trying to find the values of A, B, and C, and we're trying to minimize the differences there, we are just going to go ahead and unpack these variables now. So I'm going to name them NL for nonlinear, because we want to differentiate from the linear regression that we did above. So we need A, B, and C. So let's get that. All right, and we're going to set that equal to minimize of the sum squared error. And then when we're minimizing something, we need to give it an initial guess. And normally you can just type in any old random guess and see if it works to fit your data. But because we did the linear regression above, we already know a pretty good guess for the A, B, and C values. So what we're going to do is, there's two ways we could do it. We could go and find out the value of A underscore, or not A under, the A, B, and C values from the linear regression, or instead of taking the time to go and type in and figure out what all of the values are equal to, we can just go ahead and plug those values in. So I can just do that, and that'll just put my guess in there. And I can do that for all three of them. Save us some time, and I think it was a pretty clever way. So, there we go. Oh, didn't do something right. Oh, typo. Minimize. Still wrong. Oh, unpacking too many variables. One, two, three. Let me fix this here. Too many variables to unpack. Expected 3. Oh, I forgot that we needed that in there to get the values. So, yeah, so now we've got our nonlinear regression. So now we just have to go ahead and plot it. So we're going to go and do figure dot add scatter add underscore scatter, and we are going to set the x value equal to t. Is that a little x equal to t? Then we're going to set the y value equal to, we want it to be a underscore nl, and the nonlinear a minus, make it pretty, a minus b divided by t plus c. All right. Perfect. So, can't forget that we want this to be lines. We want the mode equal to lines, that way, because it's a model. And then we also want to name it. Let's give it a name. We'll just call this one, can you guess it? Nonlinear regression. Boom. So it's getting a little hard to see. So we have our 3 lines here now. We can see the purple, you can kind of see the red, and then you can see the green. So again, as with our fitted linear regression data, this is just connecting the points. So we can go ahead and do what we did from above and fit it with the better spaced temperature values. So we could do that really quickly. Just copy what we did up here and change it like we did before. So we just need the temperature to be tplot in here as well, and then we just want to give it a new name, fitted NL. And then just enter, and now it's getting really crowded in here, so we're going to go ahead and zoom in and take a better look. So we can see the green and red. Let's see if I can find a better spot that'll show us all 4 of the colors. Okay, I don't know if I'm going to be able to find all 4 of them, but we can now see how the fitted and the nonlinear are separate. Oh, sorry, my dog barked and scared me. Yeah, so we can see that they're both different, and we have successfully fitted the nonlinear and linear regressions. Hope this was informative. Thank you for watching.